I was kind of starting like, yeah, that's still a little bit.
Okay, I think we can probably get started. So very happy to have you, James Anderson, to give us a talk today. James is an associate professor at Columbia University in electrical engineering. And before that, he did his postdoc at Caltech. He was a postdoc there while I was a student. And then before that, he received his doctorate from Oxford University. So yeah, whenever you're ready.
Cool. Thanks very much, Lisa. Okay, so the plan today is I'm going to tell you about some work that's sort of on the less fashionable side of machine learning, but I can at least relate it somewhat to machine learning, just so people are interested. And the idea is I would like to accelerate certain system identification algorithms, and I'm going to do that by introducing some machinery from numerical linear algebra. Okay, and I'm going to introduce this in the context of learning the Markov parameters of a system and then mapping the Markov parameters of the system to a realization. Again, why am I interested in doing this? Well, there's no shortage of data, right? And systems are getting bigger, more and more sensors, they're becoming cheaper, smaller, we can put them everywhere. And there's this idea that even though hardware is rapidly advancing, GPUs, TPUs, edge devices, there are still a ton of really low-level algorithms that basically can't take advantage of the new hardware, right? They don't parallelize in any non-trivial way. And so the idea of this talk is to take some look at approximate algorithms, right? So they're not going to solve the problem exactly, but they are going to have this nice structure that allows them to be parallelized almost trivially. And if we do our job right, we should at least be able to control how accurate they are, or at least bound their accuracy. And so this idea of randomization, I just want to give you a little taster of how this can work. And then I'll get into a proper outline of the talk. But imagine that you have an n by n positive semi-definite matrix A, right? And you would like to estimate the trace of A, but you can't load A into memory, right? So typically you would, if it was small enough, you would just read A into memory and then you'd sum up the diagonal elements. Okay, but let's pretend you can't do that. So a randomized trace estimator looks like this, right? It says, let's consider a sequence of random vectors of length n, okay, subject to the fact that they're isotropic, right? The expectation of their outer product has to equal identity. Okay, and then you can show that if I create this matrix capital W that is, this scalar capital W that is just the quadratic, right? By applying the cyclic properties of the trace operator, I can show that the expected value of W is equal to the trace of A. Okay, so in expectation, I just draw this random vector, I multiply it out, and on average, I'm going to get the trace of A, which sounds simple enough, but in practice, that's going to work terrible because you don't know what the variance is going to do. Okay, so, well, what do we do? Well, let's just create independent copies and average these results, right? And I can show that if I do this L times, so now W sub I is just another realization of this W transpose AW, then my estimate is still unbiased. And I can show that I get a decrease on the variance, and this variance scales with 1 over the number of times I repeat the experiment, right? So I'm kind of getting the behavior I would like to have. And so I can sort of pin this down to, okay, what sort of distribution should I choose to draw my random vector from? And the first thing you might think to do is, well, let's just draw it from a Gaussian distribution with identity covariance. Another option would be the vector of plus or minus ones drawn uniformly at random. And for these two distributions, I can show that actually now the variance has this form where it's bounded by 2 over the number of samples and I've actually got the trace on the right-hand side. So I can see exactly how my variance is playing for these specific distributions. The nice thing about the thing that's going to come out from this, right, is, well, we could work with this Gaussian random vector, but a lot of these methods that are based on randomization, the speed at which they operate is going to be bottlenecked by how expensive it is to do a matrix, to compute a matrix vector multiplication, right? And doing that for floating point representations of Gaussian variables is actually pretty expensive. Okay, but this plus or minus one, this Rademacher vector, the theoretical computer science community and the numerical analysts, they have very fast algorithms for doing this. And I can choose other distributions that have even more structure and more complicated to write down, but I can get even faster algorithms. But the point I'm trying to make here is this idea of randomization. Randomization used to be, okay, if there's no hope of solving the problem you want, then okay, go to Monte Carlo and you get something out. And if you really work at it, maybe you can get some nice probabilistic bounds out of it, but it was really a method of last resort. And what I'm trying to convey in this talk is actually randomization can really help. This is quite a powerful tool. Another reason you might want to do this is that you can't actually access, if the A matrix, for example, comes from a computational fluid dynamics code, right, or some black box thing that you don't have access to, then you actually, draw AX is actually the only way you get to interact with it. You don't get the elements of it. Okay, so I'm going to talk about two specific randomized algorithms. These are not mine, right? My job in this talk is to act as a messenger, right? I'm trying to encourage people to take a look at the randomized numerical linear algebra literature, and I'm trying to bring it to the control side of things, because I think there's a lot of work that can be done here, and I think it can be really useful, but there aren't that many people that are doing it at the moment. So this is more a sales pitch of other people's algorithms. My contribution here is pretty minimal. But if I convince you guys to work on some of this, then I'll take that win. So we're going to start with the randomized SVD, and we'll see how this can be used for realizing system parameters. And if there's time at the end, and there probably won't be, I will show you how we've been using this technique in building a large-scale semi-definite program solver. We're then going to look at this idea of sketching, which is another sort of random projection method. And here we'll use this in a least squares sense to estimate the Markov parameters of a system. So this is probably a very insulting slide to put up, but it's probably good that everyone is roughly on the same page, because a lot of it is going to build from this. Right? So any complex matrix admits a singular value decomposition. Is there anything that I should point out that is of interest on this slide? I guess there are different versions of the SVD. So we are looking at the case where the matrix of singular values is not necessarily square. It's going to be added with zeros. So this isn't an economy SVD. This is full SVD. And just a brief recap is that the matrices U and V are unitary, right? So U transpose U is equal to identity, V transpose V, blah, blah, blah. And we're going to arrange the singular values so that sigma 1 is the largest singular value. But hopefully everyone has seen this before. So the SVD comes up sort of, the workhorse of linear algebra. It also is super useful for providing optimal low rank approximations of matrices. So imagine you are given this matrix A, and you would like to recover, or you would like to produce a matrix X that is close to it in the sense of either the Frobenius or the 2 norm, subject to a rank constraint, right? This is a non-convex problem, but the SVD, Eckart and Young showed that an optimal X can be constructed, and we know the form of it, right? You just decide what rank you're looking for, and you basically zero out the singular values above whatever your choice of K is, right? And then you form the matrix by taking the outer product of the singular vectors. So what I'm interested in is there are cases when, I should say, the cost of constructing a regular SVD, right, is order mn times whatever the smallest of the number of the row of columns is. And so for even modestly sized dense matrices, this is potentially off limits. We'll get to some examples now. If you just generate a dense, at least 2 years ago, a dense 2000 by 2000 matrix, you often couldn't run this without sort of resorting to C implementations or going to sort of high performance computing. So if I wanted to construct this optimal projection, well, I couldn't actually do this for a large matrix, right? This is sort of going to be off limits. So here's sort of some motivation for where this might be used, right? So in image compression, like this is the East River in New York. This is a full rank image. I could take the SVD. I would have to choose what level of compression I'm happy with. So I would plot the singular value. Oh, this was the point I didn't make, which I should have, is we also know what the error is. So when we're dealing with the operator norm, the error between the low rank and the full rank matrix is given by the singular value that comes after the point where you truncate. If I flip this to the Frobenius norm, the error gets worse. I then have to sum over all of the singular values that I truncate. So something I could do is I take my image and I want to have a slightly more efficient storage of it. So one way to do that might be just to compute the matrix factorization and throw away the parts I don't care about. And so I would look at the spectrum, and if I'm lucky, I'm going to have a spectrum that decays really quickly, and there's going to be a really nice sweet spot right down here, and all the singular values to the right are very, very small. I'm going to get a good error. This is an example of an image that, okay, it starts off, things look pretty promising, but then it decays pretty slowly towards the end. So I would choose a point on here, and if I take a rank 250 approximation, so I've decided this point should be okay. So I throw away all the extra vectors. This is the rank 250 approximation. This is roughly 3x compression rate, and this image, I probably should have put these side by side, but is pretty damn good. I then get greedy. I think, hey, maybe a rank 20 approximation, which will give me great 30x compression. And the image is, well, for a 30x compression is not terrible, but it's also not particularly useful. So this is one area where sort of low rank approximations are useful in terms of memory and storage. But in order to create those previous slides and figure out where to truncate, I had to compute the singular values. And I'm interested in the regime, and I'm going to motivate this by a control example later, where the matrix A is just too big to compute those singular values. So this paper is, I think it came out in 2011. It's an absolutely beautiful paper. I think it's possibly favorite academic paper that I've read. Just the combination of linear algebra, probability, and the sort of style of writing is just fun. Which isn't true for most papers in linear algebra and probability, but we'll move on. And the idea there is that instead of going for the exact singular value decomposition, we will come up with something that approximates it. And if that approximation is good enough but is cheap to compute, then I'm happy with that. And so I can use this in cases where I have either a very limited resource budget, and I want to do something on maybe an embedded device, or in the case where I just can't use the direct method anyway, and sort of approximation is just something I have to live with. And these methods, or the methods proposed in this paper, are two-stage methods. First of all, you come up with some randomized algorithm that is going to give you an approximate basis for the range of A, column space of A. You use that to project into a lower dimensional space, and then in this lower dimensional space, you use your favorite off-the-shelf classical algorithms. Okay, so the first stage is doing the projection, coming up with a projection, an approximate projection. The second stage then is use your highly optimized BLAS code or whatever you have to hand. So to formalize this a little bit, we would like to come up with a matrix Q. Right? Q is going to be a tall matrix, and the columns of Q need to be orthonormal. Right? So Q transpose is a projector. Okay, and the number of columns that as I build Q out and make it wider and wider and wider, this is going to become a more accurate projection. So the question is, how do I produce this Q in an efficient manner? And this is where the randomization is going to come in. And just to make a few things clear, when I say I want something, so this projection should approximate A, I mean that in the sense that the norm between two norm between A and QQ transpose A is less than some parameter epsilon that I decide I can live with. And so the idea is like embarrassingly simple, but the proof and the work that goes into showing that it, again, not mine, but the work that goes into showing this works is really quite striking. So the algorithm, right, I want to build an approximation for the range of A. So what I can do is I can draw a random vector, omega, and I'm going to be slightly cavalier with what I mean by random, right? So just for the purpose of this talk, just think each element drawn IID from a Gaussian 0-1 distribution. I'll tell you in a few slides' time why you might not want to do that and how you can do better, but this is sort of intuitively what you should think about. So I'm going to draw this random vector omega, or omega I, and I'm going to compute A times omega, and I'm going to store that vector Y. And then I'm going to do it again. And then I'm going to do it again. And then I'm going to do it again. And I'm going to do this if I want, say, a rank 10 approximation. Well, I'm going to do it 10 times, and then just for good luck, I'm going to do it an extra 3 times. I'm going to slightly oversample beyond the target rank that I want. And so in matrix notation, I'm just going to stack my column vectors y1 through k in this matrix Y and my random vectors in this omega matrix. And this is the thing that's kind of super important to why this can be done really, or one of the reasons why this can be done really quickly. I can perform this matrix vector multiplication on a different machine. As in, I can do this in parallel on 10 different GPUs or CPUs or devices. This does not have to be done centrally. So once I've got this matrix Y, I'm then going to construct a basis, right? And the idea is that a basis for Y, if I do it in the right way, is really sort of capturing most of what A is doing to a vector. Right? It's trying to capture the action or the range space of this matrix. Okay, so Y is sometimes called a sketch of A, and the crucial point here is that K, right, the number of the target rank and subsequently the width of the matrix Y is much, much smaller than M and N, the number of rows or the number of columns. Okay, and these algorithms work best when M and N are really huge, right? If you can compute an SVD directly, do that, right? But for cases where you can't, and I'll show you some in a few slides' time, this is really important. Okay, so the first stage, I'm going to draw this random matrix omega, and I'm going to draw, so I want a rank K approximation, but I'm going to take L is equal to 5 or 10 extra samples. Step 1, I form the sketch matrix. Okay, and the cost of that is roughly order mn times the number of samples. Okay, I'm then going to, there are many ways you can construct a basis, but I'm going to use a QR decomposition. except I'm not going to use a full QR decomposition, right? I don't care about the R matrix, right? You know, the triangular part. I don't need to keep or even compute it. And it's the economy or the thin version of the QR factorization, right? So this is only providing a basis for the range of A. It's not building up the basis, the orthogonal basis for the null space. And the cost of this is now n times k plus l squared. So the first time you see this, it's kind of amazing, right? The dominant step so far is not the QR decomposition, it's the matrix vector multiplication. Right, and so mn k plus l, this is the cost if I'm multiplying a dense matrix by a dense vector. Right, if I'm not going to get into the details, but I can draw very, very structured random variables that the computer science community has created incredibly fast matrix vector multiplication primitives. Not only are they theoretically fast, they also have like really rock solid implementations. So this step is absolutely crucial. And so this is the theorem from Halcombe, Martinson, and Trop. It looks kind of complicated at first, but it's really pretty straightforward, at least the explanation of it. Right, so this is the expected error between my projection and the original matrix. Now, if I cover up this bit, right, then I get 1 over 1 multiplying sigma k plus 1. This is the theoretical, or this is the optimal deterministic case, right? If I could actually type SVD and right? So this part of the bound is really now a function of the size of the components that I'm working with. That is the rank I'm targeting, the size of the matrix, and this oversampling, right? So the way to interpret this is by moving to this stochastic approach, I pay the price of a small, it's a relatively well-behaved, I guess you'd call this polynomial additive term in terms of the error, the optimal error. And it's doing better than this is pretty tough, right? So just to go through this, K is my target rank, L is my number of additional samples. And this is never really more than like 5 or 10. I'll show you that these parameters don't make too much of a difference. All right, so the question then becomes, well, is this error is this good enough? And what I will show you is that in certain control pipelines, actually, this error behaves very well. So a few comments are in order, right? If the spectrum doesn't decay particularly quickly, like the example for the New York City image I showed you, it decays, but not as rapidly as you might like. There are things you can do to boost the speed of the algorithm. Again, this goes back to sort of classic numerical work. You can introduce power iterations where you just take powers of AA transpose. And essentially what happens is the singular vectors remain unchanged, but the singular values scale by the power to the power q, right? So anything below 1 gets smaller quickly, anything above 1 gets blown up. And so if you do that, then the error bound, right? This, I'm not sure what that is, but this right-hand side changes slightly, but you're still in a pretty good position. But this gets rid of some ill conditioning. You also don't necessarily need to decide the rank you want ahead of time, right? So K came up in the previous bound. Here you can actually start from like K equals 3, 4, 5, and you can, I'm not showing the error bounds, but you can actually predict the error ahead of time, and the algorithm just terminates once you reach a desired level of accuracy. I'm not showing that here, but it's very it's straightforward to do and implement. And so stage 2, okay, now I've got this projection. How do I build out the SVD? Right, so this is now everything is deterministic. So at this point, Q and Q transpose have come from stage one, so they're given. The approximation I have, this is bounded by epsilon. So what am I going to do? Well, the first thing I'm going to do is I'm going to multiply Q transpose by A, and this gives me this much smaller block. Okay, and then I'm going to apply the classical SVD now to QA. Okay, so I'm going to get the notation is slightly bad here. This is going to be a new U, is new sigma and a new V that is exact, or at least exact numerical precision for Q transpose A. Right, so this is going to be, and this is why it's super important that K is small, because the smaller K is, the smaller this block is going to get. But now I can just go to MATLAB and type in the SVD. So I do that, and then I shuffle things around a bit, right? I multiply Q by U, put that in that block, and now this is my approximate SVD. Okay, so all I've done is shuffle things around down here. So Q transpose U, this is my approximate original U matrix. Sigma is my diagonal matrix of singular values, and V is my right singular vectors. Okay, and this satisfies the fact that these matrices are now unitary, or rather semi-unitary. Okay, so stage two is, again, just matrix vector multiplication, and whatever the cost is of doing an SVD on this much, much smaller dimensional Q transpose A space. So what does all of this cost in total? Well, the dominant cost is computing A times omega. So this is going to depend on how big A is, and it depends on your choice of random variables. So there's a specific class of these random vectors called subsampled random Fourier transform vectors that sort of provide, they satisfy the statistical requirements, and they emit a very, very fast matrix vector multiplication. And so if I compare this to other sort of classical methods, if you like, then if you use a Krylov method, first of all, you have to read the data in a lot. Okay, and so that's expensive. Here, you only have to do it. It says once, but it should be twice. If I was to try and compute the truncated SVD, so this was actually compute the original SVD, this is going to be a lot more expensive. So actually, the RSVD is, in terms of both space, it's consistent with existing algorithms in terms of the number of times I have to load my data into memory. I have to do it far fewer times, and the time complexity is actually better than the alternate methods. So moving over to system ID. And so imagine we collect some data from a dynamical system, and we get to choose the input that goes in. We observe the output, and so we watch what the system does, and we can repeat an experiment multiple times and collect a bunch of trajectory data. The goal is now to construct a state space realization represented by a linear time invariant dynamical system. So one way of getting from data to an estimate of the model would be to first run some parameter estimation algorithm that allows you to compute the Markov parameters of the system. And then once I've got the Markov parameters, I then need to, these appear as product of the matrices I care about. I then run a realization algorithm that then sort of extracts the A, the B, the C, and the D matrix from the Markov parameters. I mean, I get the D matrix for free. I just read it off. But I need to extract A, B, and C from these products. Right? And this keeps going, right? This is C, A squared, B, C, A cubed, B, up to, depends on the length of the experiment. All right, so to make things a little bit more concrete, we're assuming that there is some underlying model takes the form of an LTI system driven by an input U and some noise process. We will assume that the noise and the control input is uncorrelated and comes from these sort of standard normal distributions. We're allowed to run n experiments, right? So you set the initial condition and input, watch what happens, and repeat this n times. So we have multiple trajectories, and we're going to do this. The length of time we observe each experiment for is going to be capital T. And so our objective, this is now a classical control problem, is to find matrices A hat, B hat, C hat, and D hat that best fit the observed data. And so ideally are close to this ground truth model, if that's where it came from. So I'm actually going to start from the bottom part of the pipeline. Right, so I'm going to pretend that I have this and work on the realization first, because that's where the randomized SVD comes in. I'm then going to look at a different randomized algorithm for doing the parameter estimation in a minute. Okay, so the idea here is we've obtained this Markov matrix G. Potentially, if there is, the algorithm sort of proceeds as if there was no noise injected into the system. Until you've given the statistical assumptions on the noise, that's fine in this setting. We're going to do everything on the noisy version of G, and you just kind of hope that it works out. You can show that it does if the distribution is friendly enough. And so we want to go from this very large matrix down to individual realizations A, B, C, and D, and show that these are in some sense good estimations. So this is in no sense a new algorithm, right? This is the Ho-Kalman algorithm. In terms of assumptions, it's fairly minimal. It assumes a minimal realization. And it assumes that the rank of this Hankel matrix, which we're going to build, is of a certain size that is bounded by the length of the trajectories you collect. So the first stage in the algorithm is to take G and just construct this, just sort of tile this Hankel matrix, construct this Hankel matrix by tiling it from the elements of G. And sort of by assumption of the minimality assumption and this second bulleted assumption, then both the full matrix H, and if I ignore the final column, which are this part of the matrix, we'll call this H minus, both of them are going to be full rank. And so the name of the game is really, how do I go from this now to extracting A, B, and C, right? I get D for free. I know how many inputs I have. I know how many outputs I have. So that tells me how many columns from G I need to extract in order to get D. So now I just need to figure out CB, CAB from these. Okay, so I can factor this Hankel matrix, or rather the first, the matrix excluding the final column, this way. And I can do this because of the full rank assumption. And hopefully you'll recognize that this is nothing more than the observability matrix and Gramian and the controllability Gramian, right? Then we can relabel this O and this Q. But how do I come up with this factorization, right? I'm telling you can do it, but where does it come from? Or rather, Kalman is telling you where it can come from. And it turns out the thing to do is you compute a truncated SVD of this matrix. Right, so I'm going to tell you, if I knew how many states there were in the system, right, if there were n states in the system, then I would compute an n truncated SVD of H. And I would do that. I would get U sub n, sigma sub n, V sub n, and I would construct, you can show that my observability and my controllability matrices are then constructed from this. And then the final stage, I can now extract A. A little bit of linear algebra shows that this is how I would then extract A. Right, and the nice thing about this is, as soon as it's in this form, right, as soon as I've got this factorization, well, now I can just read off C. So I get C from here, I get B from here. And the final, sorry, this has got the story in the wrong order. The final step here is how do I get my A matrix, right? And again, it's a few lines of linear algebra to show a bit more than that, but it's straightforward to build out the A matrix. Okay, so now I've got an A hat, a B hat, C hat, and a D. So again, a few comments are in order. The realization problem is a non-convex problem, right? It's a matrix factorization problem. The algorithm that I just gave you is sort of agnostic to the coordinate system you want to use, in the sense that the realizations are unique up to this coordinate transformation, right? So for any invertible t, the algorithm can't really distinguish between A and TAT inverse, B and TB, blah, blah, blah. The computation of this is dominated, well, it is nothing more than the cost of the truncated singular value decomposition. The robustness guarantees, I guess these are Michigan results, this is Neshmieh, showed that effectively the difference between ground truth and what comes out of this algorithm satisfies this nice scaling bound in terms of so the error is controlled by 1 over n, which is the number of experiments that I do to the power 4. So if I want to drive this error down, this tells me that if I add a few more experiments, this error is going to decrease pretty quickly. So I'm going to do exactly what you think I'm going to do, right? I'm going to replace the truncated SVD with a randomized algorithm. And the result is immensely pleasing in the sense that it works well in simulation. I'll show you some in a few minutes. But essentially, we can drop the computational complexity by a factor of n. So this is, so it would be pmn cubed. We can get it down to pmn squared log n. And the error bounds that Neshmieh and Samit developed basically remain untouched when you pass through the randomized approximation. Right, so the results, and I appeared to be showing you the wrong version of the presentation because there was a bit more of a voila factor.
Yeah, a good question about the error bounds.
Yeah.
But you're doing something randomized. On the previous slide, you had like error bounds and expectation and variance.
Yep.
And
I haven't got to the stochastic error bounds yet. They were so I will come back to it. Yeah, so this was supposed to display in 2 parts, and I could say, hey, look how fantastic this was, but I guess the cat's out of the bag, right? So for here, I've run 6 examples. We've averaged over a bunch of examples, and we're increasing with every row, we're increasing the state dimension, the number of inputs, the number of outputs, and the horizon of the observation that we run. And I'm just writing down now, this is the dimension of the Hankel matrix that we construct. And you can see that once we get to around 120 states, we can no longer, if you type SVDH in MATLAB, the computer starts getting hot, the fan starts running, and then all of a sudden your computer crashes. In terms of the randomized algorithm, Right? What's taking about 900 seconds to do exactly takes less than 5. And what in the realm where you can't actually do it, we're sort of at around the 20 seconds to a minute mark. And so then the question is, well, is the error any good? I mean, we had the theorem that I skipped some of the details on, but I told you the error bounds basically go through. So if we consider the error to be the normalized error in terms of the H infinity norm between ground truth and what your algorithm spits out, normalized by the norm of the true system, then we see that our error is comparable across all system realizations. In terms of the algorithm parameters, of which there were a few, right? There's this oversampling parameter. There's the number of power iterations to execute if the spectrum doesn't decay. Here is a slide showing what happens when, so what I'm showing on the x-axis is how the oversampling parameter affects in this plot the runtime, and it effectively doesn't, which shouldn't be that surprising, right? I'm only doing, in this case, an extra 10 matrix vector multiplications. But it also doesn't seem to have too much of an impact on actually the realization error. Again, so the point I'm trying to make here is, despite the fact there are parameters to this algorithm, the algorithm at least seems to be pretty insensitive to them, so you don't need to spend a lot of time parameter tuning. In terms of what does the spectrum of the Hankel matrix actually look like, do we need to, are we in like the New York City region where it goes slowly, where it goes quickly and then slowly and then quickly again? Well, one way to test that is we can start looking at what happens when we play around with including power iterations. And so what this plot is showing is that as I start adding power iterations, the runtime changes by, and this is for the 100-state system, by sort of less than 10 seconds. So it's not really, doesn't really have any real impact on, it's very much getting a sort of a linear increase, but with a relatively small coefficient. And the error does, the realization error actually does come down. So this suggests that the Hankel singular values decay quickly, but perhaps not quickly enough. After, if I extend this plot out, then actually it saturates around here. So we don't really need to do, including a few power iterations is going to help, but it's not going to help by a lot.
Quick question, I missed, like,
Yep.
where are you using power iterations?
Yep. So, right. So instead of working with sampling A times omega, if the spectrum of A is slow, I work with this matrix W, right, which is AA transpose QA. And so that Q, as I increase the Q, that changes W. That's where the power iterations come in. So then I sample W times omega.
You still, like, how do you compute?
Pardon?
Is it an efficient thing to?
Yeah, that's what I'm showing. It doesn't, at least for when you're not working with millions or billions of variables and just hundreds of thousands, it ain't going from, so that would be this graph, right? This is the increase in computation time. It goes from 4.5 seconds with no iteration to 8 with 4. But the realization error, the scale here is one, but if I increase the number of iterations, this doesn't get any better. Okay.
Follow up on the power iteration, you're basically, you multiply by A, then A star, A star, you just keep doing that 8 times. So let's say you had a black box simulator, so I have an A.
Mhm.
In general, is it easy if I told you that the system is linear to get the adjoint to do the A star? Or is that,
That's a
you
good
can do it
question.
in this case, because you know what the A is, you can get an A star and do that calculation.
Yeah, okay, with the,
That's step, a non-general step.
that's a really good question. If it's coming from, So I mean, if you know it's coming, like writing down the adjoint of a linear dynamical system is straightforward to do, but if it's coming from something from a nonlinear, that's going to be tough. It's going to depend. Yeah, that's in general, it's going to be hard. Yep.
So, your example here is for a finite dimensional system. So your ground truth is a finite dimensional A. And I'm wondering.
Or something that, or something that can be very well approximated by it. Yeah.
The actual Hankel matrix has finite rank.
Yeah.
It has a fixed rank that's like something, right?
Mhm.
So you do have all the singular values after that, ideally would be 0. I'm curious if you still have the same insensitivity to the oversampling parameter. If you have, for example, you're using data from, say, a solution to PDE or something where you don't have finite dimension. So no matter how big you make that that Hankel matrix, you always have a full set of non-zero singular values.
So discretization of the PD was, as far as I'm aware, one of the motivating examples where a workflow like this is really targeting. So I haven't personally looked at it that way, but to the best of my knowledge, then it shouldn't be a problem.
The only reason I ask is just that I mean, something I've found in the past is that if you have an infinite dimensional system, you have a full set. It doesn't matter how big your matrix is, that singular values are all non-zero.
Yep.
You need to make that matrix much bigger than the final order that you want for your reduced order model in order to.
Yes, that's true. Yeah.
That's why I was asking about the oversampling.
The oversampling is more about getting a good basis approximation. So in high, so this is really targeting high dimensions. So in high dimensions, when you draw these random vectors, you kind of hope, the idea is that they're going to be in general position, but you could be unlucky. In high dimensions, every random vector is sort of approximately orthogonal or close to orthogonal. But on the outside chance that doesn't happen, the oversampling will then correct for it. So that's, as I found out this morning, Laura knows far more about this than I do. So in fact, I think she was teaching a class on this morning. So yeah. Okay. So the second part of the talk, and I'm definitely not getting to the third, but that's fine. Yeah, I know. I was going to say this. The second part is really much quicker, right? So the second part is obtaining these Markov parameters can be solved as a least squares problem. And so there's this nice idea called sketching, where instead of trying to solve this problem, right? So A is now a tall matrix. Why don't I produce a really wide matrix and pre-multiply AX minus Y? Right, so this is projecting down into a much lower space and solve the problem in this space. Okay, and so what I can hope for is if I call X hash the optimal solution to this problem and X star the optimal solution to this problem, well, X hash is always going to be greater than f of X star when I take the solution here and plug it in here. By definition of optimality, it has to be. But what I can hope for is some suboptimality guarantee where maybe it's bounded by 1 over epsilon squared f of X. And it turns out, so this raises lots of questions, right? How do I choose S? What is the dimension that S should be? Well, it turns out that the optimal dimension of this matrix S, remember my choice of X, if I go for a really compressed thing, is going to give me a worse solution, but the best choice of S, it will have m rows, and it depends on 1 over epsilon squared. So there's going to be a trade-off, and Mert Palenki and Martin Wainwright showed that actually this is doing this for a wide class of least squares problem is a bad idea, because in order to get the right scaling on the S matrix, any savings you think you've got are now brought back in by the matrix vector multiply And so you don't actually get around the scalability problem. What they proposed is instead you can rewrite your problem in this form, right? And then if you were to take some Newton steps to solve this, I'm writing it down for the unconstrained case, but you can do the constrained case, right? Then why don't you apply sketching to this part of the problem, so the part inside the norm, and leave the inner product alone? And so now what you're going to do is so by sketching this, and in order to reduce the variance, you're going to do this q times. So q different processes are going to solve this problem. It's just the algorithm. Then actually the choice of S and the choice of randomized variable, you actually can get a win. You can beat this sort of trade-off that the original sketching idea sort of failed to pick up. There's a lot more to be said on that, but essentially we can now take our Markov parameter estimation problem and write it as a matrix least squares problem in the Frobenius norm. I'm not writing down exactly where the matrices come from, but U and Y are basically Toplitz matrices of the trajectory data. The naive method for computing this would be a QR decomposition, something, which again isn't going to scale. That's the point. And we were able to show that provided you observe, perform enough experiments, then we can tell you what the dimension of the sketching matrix should be, right? As long as S is larger than this number, the details, again, the details are important, but for the message I'm trying to convey, the theorem tells you how to choose the sketching matrix S, and it comes with this finite sample bound that tells you after running k iterations of your sketching algorithm, then the error between the solution, if you were to terminate there, and ground truth has this nice geometric decrease, right? So the error is getting small very fast with this, with high probability. So I'm just going to show you some plots. Right, so this is a 40-state, 30 input, 20 output example that corresponds to around 45 million data points. And so the question of what sketching matrix should I choose? Well, if I just choose elements from a uniform distribution, that's not particularly fast. The error still decreases okay, but it's not great. If I make it slightly larger, then we get this much, much faster decrease. But effectively, any of these, the scale on here, right, this is, the loss function is 10 to the minus 14, right? So as soon as, realistically, as soon as you're kind of around here, you're happy. And in terms of wall clock speed, which I appreciate isn't the greatest metric, but this was really very fast, around the 5 to 10 seconds. You can also come up with hybrid sketches where you first pre-multiply by a sketching matrix from one distribution and then another, and that works very well, although this is not the slide I'm talking about. Again, this is now how does the number of workers, or sorry, the number of affect the plot. And this is now where I'm going to end, but effectively now what we've shown is that these randomized algorithms can be used in, or two different variants of randomized algorithms, right? The randomized SVD and Hessian sketching can be used in the two phases of the pipeline, of the system ID pipeline, and they allow you to compute pretty good approximations for systems like of orders of size, for magnitudes of sizes larger than what can be computed if you just try working with the data directly. So I'd also like to say I've skipped almost all of the theoretical results in here to try and convey the ideas. They do exist and they are in our paper. The real fundamental results come from the two papers that I referred to, the Halko Martensen and Trop paper and the Palanki and Wainwright paper, as well as Neshmier's paper for the realization algorithm in the deterministic setting. And so with that, I will end. And if there are any questions, please. 5 minutes.
Quick question. I was curious about the third part that you didn't cover. Is there a
Uh,
sentence summary of?
Yeah,
like
sure,
all the
absolutely. So here's the one sentence summary, right? We wanted to build a semi-definite programming solver to solve large LMIs that arise in control of really any problem that is solving a conic constraint. And there are many families of algorithms that rely on efficient projection, right? Projected subgradient, ADMM being 2 examples, right? And these algorithms work really fast when the projection is quick. And so what we can do is we can use the randomized SVD. So in the projecting onto the positive semi-definite cone is an eigenvalue problem, not an SVD problem. So I lose this because as soon as I take the singular values, I lose the sign of the eigenvalues. So we came up with a transformation that effectively allows you to gauge the sign of the eigenvalues, and then a little bit more to it than that, and then we can map this to the SVD problem and use the randomized SVD to speed up an ADMM or projected subgradient method for solving linear matrix inequalities. And so we've applied them to sum of squares problems, and there's very much work that is ongoing. So it's actually convenient I didn't get to the numerical results because they're not as sharp. So.
I have a quick question. Very cool, first of all, because some of these results myself, they are outside of my scope. So very nice to see. Thank you. In regard with the last part that you saw, the sketching approach, right? Still, I see that you need to take a lot of inverses. Are we worried about that, or you need
No,
to take this inverse
not
this
so much
matrix,
if
or the matrix? Are they going smaller? I don't remember the formula.
it's not the dominant cost.
Okay, yeah. This at the end that was the question.
Yeah.
What's the dominant cost? Yeah.
Yeah,
But they are-
not the inverse. Yeah. Yep. Oh, sorry, can I just, and one other thing, this is Newton's method, so it's a second order method, so you generally don't need to take many steps either, right?
I see.
It's not like SGD where, well, there's no inverse in SGD, but it's not one of these first order algorithms that you need 100,000 iterations to get
Yeah,
up.
just I was wondering what's the dominant cost here, because many times, yeah, inverse.
Good question.
Thank you.
Sorry, Lisa.
Where's this ID? Maybe I lost track of it, but when you were talking about like how many sketches you would need or something like that, around slide 36, I noticed that the number you needed did not include n, which is the size of the state, and I was wondering whether I just missed. Yes, if it was in there somewhere, so small n, right? So the number of rollouts depends on the size of the input, but not the state. Is this correct?
Yeah. Which is somewhat surprising.
Yeah, it is.
Maybe there are some on the chat.
Oh. No, everyone understood absolutely perfectly online. Michigan students are very good.
This was quickly.
Okay, well, if there's no more questions, let's thank the speaker again.
They were asking the hard work. Happened that our students are really good. With my lunch committee, the question is.
I noticed that you have an appointment in DSI as well. Did they decide? That's, I don't know. DSI actually, there was headlines of
So, I'm not sure about Monday, I will see, because yeah.
And that money went away. Yeah, it sounds like that's less.
Now it's more.
Yeah.
It's good having the house, because it's taking care of the baby. Yeah, I know. It was like. But it's amazing. On Thursday or Tuesday. Yeah, they can. Okay.
Like I'm just.
When you're back.
Lecturer role in computer science, but I think the goal is basically to teach pretty much entirely massive classes, master's data science. Yeah, and I spoke to Gaurav, the director and chair, or whatever, and he was saying that there seems to be like some attention on kind of revamping that curriculum. Yeah, so you can do it like. So yeah, there are like certain core classes. I teach a bunch of classes. Yeah, data science. So I teach a data science.
It's the younger generation.
I was surprised.
That's. You can see I live with the bigger long line, I can have a much more initiative.
Yeah. Yeah.
And she said. Significantly, like.
Necessarily.
It's robotic technically, but
You can keep
Okay.
Yeah.
The Congress to release the money for the Israeli startup project. No, I wasn't. I just. From the essentially, they were informing us what's happening in the Congress. Since March 16, they're going to pull for the parts and the startup project. So essentially, I sent this email, but yeah. So I think we'll be waiting for quite a while. Yeah, we'll wait even.
I'm just coming after.
I will see you later. Yeah.
How was the talk?
I'll drop you an email.